Okay, let's say if you have a sample application, a simple application like this is the example I'm going to show you the demo. Let's say you want to use MATLAB or Mathematica to run, I don't know, a simulation, but you don't need MPI. Then you can use directly Condor. You just need to write a simple description of your application, like specify the application, the arguments. The universe is important because vanilla means the standard universe. You don't need anything special, just the normal environment. So this is for normal jobs. Okay. You also have to specify the output files, the file where the error will the standard error will be saved, and you also have the log of generated by Condor. So this is a typical job description of Condor. Okay, you can check the status of the job using normal Condor commands like Condor Q. I'm going to show you in the next few minutes. Okay. Regarding the API submission, it's a bit different because, as I said, the setup is a bit more complicated, and for this we offer support for generating automatically. It's our InfraGrid API runtime, InfraGrid API application that generates every that's needed to run the application, but also provides an important feature. The important feature is that it's able to capture the API trace. So it captures all the calls to the API library and gets information about performance. This is an example usage of the InfraGrid API run application. So basically we have three arguments. One is specifies the number of processes you want to be scheduled. It's up to Condor to decide where the application run. Okay, we have another flag that requires that the trace file should be generated. This trace file can be used with Intel Trace Analyzer for analyzing the performance of the application. Okay, and the last argument -c specifies the command to be run to set up the API cluster. Okay, like always, you can check the status of your application using Condor status, Condor Q, and so on. Okay, regarding supported applications on InfraGrid, as I said, we support being let's say, a normal cluster based on InfraGrid architecture. We support almost any kind of application. Natively, we support applications that have been built for Linux 2.6. In case you have binary applications, I think that GCC is 2.4. So I think that most applications have been binary form to be run in our cluster. Okay, as an example, I gave an example with two commercial applications that can be installed in this cluster if you have a license for. So we don't provide MATLAB or Mathematica, but can be installed if you have a license. It can be set up. You can install it manually in a home directory. Okay, another type of applications that will be supported in the near future, but now we don't support, scheduling virtual machines. For example, you have an application that runs only on Windows. Sometimes, let's say in the near future or short future, we are going to support running virtual machines. Let's say you have your application that does a simulation. It's an application, Windows application, let's say SPSS or something else that doesn't work on Linux. You write your code for Windows, create a virtual machine, and give it to Condor. Condor will deploy it somewhere on the cluster. So this is another approach, but the overhead is much bigger. The performance you can expect for running a simulation in a virtual machine is far less than a normal application. First of all, because you won't be able to use, let's say, if you use InfiniBand MPI inside, you won't be able to use InfiniBand. So you don't have access to the low latency network. So this is a feature we are going to support in the near future for Windows applications. Okay, now I'm going to make a demo or show you how to use the cluster, and after I'm going to finish this presentation, we are going to do a practical. So you will be able to play with the cluster by yourself. Okay, these are the information that I will show you also after this presentation. Is the access information. So I'm going to connect to the head node that's called head InfraGrid. In Windows, you can use Qt for connecting. Okay, the username that's available only for today for this presentation is iGuest from InfraGrid Guest. Okay, and the password is raw UBT info I'm going to connect to the Red Infrared node using SSH. As you can see, I'm using Linux, so it's more simple for me than for Windows to connect to the head node. In case you use Windows and you want to use the graphical tools like the Trace Analyzer, you will have to set up X-Server on Windows. I think we're going to write a tutorial for setting up this on Windows. So you need X-Server, and I think that's all. So X-Server running. Okay, now I'm connected to the head node, and I'm going to download an example I prepared for another session for students. Okay, this is like a classical example for an API application. It's computing the value of P using Monte Carlo methods. So I think it doesn't have any practical. It's not useful in practice, but for showing the principles of exchange data, it's more than enough. Okay, so this is the basic layout of application developed using CMake. This application was developed in order to show how to build an application and how to use the tools. Okay? So first of all, I'm going to show you the layout of the code. I'm going to use the net command. Okay? So first of all, we have the source code for our application. There are two C files, and the rest are backup files. Okay, this is the main application. Also, as an example, it doesn't use directly MPI. It uses the Boost library, maybe you know it. The Boost library provides, it's a C++ library that provides abstractions over, let's say, really big number of different libraries, and also they implement advanced mathematical routines natively in C++. It's basically a template metaprogramming library. I think it's a bit difficult to use by beginners, but by let's say medium C++ users, it's really accessible and offers great advantages. For example, this application uses the API router from Boost and also uses a library for program options. I will show you. Okay. And it uses random number implementation from Boost. This example, just an example, we use the percent history implementation. Okay. If you want, we can discuss the layout of the code. Basically, as you can see, we don't make any direct calls to MPI. We make calls to the Boost API library. For example, we don't do API init. We use MPI environment from Boost that sets up everything. For exchanging data, we can use, for example, we can use normal C++ structures. In this example, we use a normal vector from the standard template library. This you cannot do with the normal API implementation. You need to do lots of casts, use primitive types. Boost has some magic inside to detect this and compile it. We don't have to use recompilation tools that analyze the code. We just use the code provided by them and they do everything behind the scenes. The code is really complicated, but what is exposed to the user is simple. So we don't see the code inside. And overhead it's almost zero because everything happens at compile time, not at runtime due to C++ template expansion. So it's metaprogramming for the MPI wrapper. The same thing is also for the mathematical routines. Okay. We have another. This is for extracting random data, the seed for the random number generator. It's not too important. Okay. And the most important part regarding the build is the description of the application. As I said, we recommend usage of CMake. CMake requires, let's say, a make file, but not a normal make file. It's called CMake list. Okay. And in this file, we specify our sources, what kind of libraries we need, and eventually we specify compiler flags. In this example, as you can see, we give a name to our project. Okay. This is is needed because CMake also offers you the option to generate Visual Studio projects, for example, or Eclipse projects. So you can develop it on Windows. Everything happens the same way as in the cluster, but instead of compiling with the compilers on the cluster, it uses the Visual Studio compilers. And you can do whatever you are used to in Visual Studio, Qt Creator, or so on. Okay. As you can see, we specify that we require MPI. We don't do anything else. So the compiler we are going to use, the only one we're going to use is CMake, nothing else. It will detect automatically the library. We don't have to say where is the library located, what kind of library to use, and so on. We need to say that, okay, we need MPI, and we are sure that it's required, because CMake also gives us the possibility to have optional libraries that change the, let's say, if you want to build your application without support for one feature, you can disable it and CMake doesn't detect the library necessarily. Okay, so we detected we want MPI to be available, and after that we say that, okay, we want to include, to have access to the header files from that location. We say that, okay, the include directories should include the MPI include tag. Okay. This was just an example, okay? And the next thing is we say that we need Boost, and this example uses a specific version of Boost. We can have, let's say, 10 versions of Boost that have different features, and we can select one based on the version. For example, we want Boost version 1.4, 1.4, okay? And CMake will detect automatically this. We don't have to search for the appropriate Boost library and so on. Okay. We can also control whether we want to link dynamically or statically to a specific library. I didn't do this for the API because it doesn't work due to interest compiler constraints. So because of this, we don't need static link here. Okay, but Boost this link static. The next thing is to say where are our source files. We say our source files are variable. Our example is API resources. Okay. In case we use the IPC compiler, we provide some additional flags. This is going to run only if we use the IPC compiler. And after that, we define the runnable and the library that should be needed. Okay. So how are we using CMake? CMake generally needs to recommends to build outside your sources. For example, I'm creating a new directory. It's called build, and I'm going to ask CMake to build our project. I have to give the path to our project. In this example, I give the parent directory. It will detect automatically the compilers. For example, it detected this compiler is GNU again. It also found, as asked, it found the API library. Okay. It found the Boost version requested. Okay. And for some libraries, for example, it has the options to only select a part. For example, for Boost, I only needed program options, random, and API numbers. After we run the application, we can see that it generated automatically a make file. So CMake, it's a meta mode. It generates make files or Visual Studio projects or make files for other make implementations. After that, we can just type make and we have an application. Okay? So we got our application. If you, for example, I'm going to remove the generated files, and I'm going to request, I'm saying to CMake that our compiler are the intercompilers. So the C++ code is missing. Okay. This time we can see that it identified correctly the compiler, that's intercompiler, set up the paths correctly, also detected the libraries.